I hope everybody is fine. And what we have discussed before is ionization chamber. We have discussed proportional counter. We have discussed GM counter. And now we would like to talk about this scintillation counter. And what happens, basically in this case, is that when an electromagnetic radiation, when it falls on certain material, suppose I have a material and some radiation falls on this material, and what can happen is it can emit light. The material can emit light due to the phenomenon what's called as fluorescence. And the incident radiation, say for example, gamma rays, what they do is they excite the atoms of this material on which these gamma rays fall, and they fall on this fluorescent material, and 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 the atoms of this fluorescent material, they de-excite in a very short time, and it results in the emission of a photon that we have in the visible or ultraviolet part of electromagnetic spectrum. Now, such a material that we have, such a material is known as scintillator. And the photons that are produced by this material, by virtue of the radiations falling on them, we call them as scintillations. Scintillations. Now, this scintillation counter that we are going to talk about, it is basically a device which is used to detect alpha particles, beta particles, and gamma particles by means of this process, what's known as fluorescence. And, and the scintillations so produced, they are converted into some amplified electrical pulse by means of a photomultiplier tube. And then these pulses are electronically detected, they are counted, and all those things are done after that. Now, what's the point is that let us go with a rough sketch of this scintillation counter, and the selection of a scintillator that we have, it basically depends upon the radiation type, the type of radiation we are interested to detect. And if we talk about alpha particles, for alpha particles we have zinc sulfide, ZNS, as a scintillator, in the form of a single crystal, in the form of a crystal, in the form of a single crystal. And similarly for beta particles, we make use of a crystal made of naphthalene crystal. And and in case of gamma detection of gamma rays, we make use of sodium iodide. So it depends on the type of detection that we have to choose. In accordance with the type of the radiation that we have to choose, we choose this scintillator. ZNS for alpha particles, naphthalene for beta particles, and sodium iodide for gamma particles. Now, let me try to draw the rough diagram of this what's called as scintillation counter. What we have is we have a tube, and this tube is called as photomultiplier tube, and then what it has is it has so say this is 1, this is 2, this is 3, and this is 4, and this is 5, and this is 6. And these are electrodes, and let me name them as 1, 2, 3, 4, 5, 6. Okay, and then what we have the closing, and here we have an anode. Okay, I should write down have an anode. And what we have is this anode is grounded, and you must have a resistance that will register the signal. Then what we have is a capacitor for filtration purpose. Then we have amplifiers, and then we have discriminators, and the things that fall into the domain of electronics, where we can count the radiation, amplify them, and can register them. Now, so what is here is that we have a resistor R here, and then we will have to connect it to the shield. But here what we have is this. We have a high tension battery, and its range is 1200 volts, and what we have, these electrodes, they are maintained at some potential. This the first one is at 200 volts, the second one is at 400 volts, and then what we have is 600 volts. Then we will have here 800 volts, and on 5 we will have 1000 volts, and at 6 we will have 1200 volts. Okay, and we have to have a scintillator, and this scintillator has to have the covering, and here what we will have is the incident radiation. So this is scintillator, this is the crystal, or the scintillator. So incident radiations will come from this direction. Now this is the rough diagram of this scintillation counter, and what we do is we have to make sure that we make use of a suitable scintillator, and this scintillator crystal is basically connected to this tube, and this tube is called as photomultiplier tube. Photomultiplier tube, and through a small pipe, that we have here, and this crystal is shielded. It is shielded by aluminum, and the radiation that's entering the crystal, it produces tiny flashes of light due to fluorescence. And what's fluorescence? Fluorescence is basically the transition of atoms and molecules. I mean to say, the atoms and molecules are first excited and then de-excited in very short span of time, of the order of 10 to the power of minus to 10 to the power of minus 9 seconds. Now, this phenomenon is referred as fluorescence. So what we have fluorescence due to the scintillator that has been fitted here. Now the photons travel the pipe. They travel this pipe and to the photomultiplier tube. They reach to this photomultiplier tube and fall on this transparent photosensitive layer. And here we have a photosensitive layer. Okay, and this photosensitive layer. Okay, and what happens? The electrons are ejected. The electrons are ejected, and the tube that we have, it has many electrodes that you can see here, and all of these electrodes are called as dinodes. We call them dinodes in a photomultiplier tube, to which progressively we have higher potentials, 200, then 400, 600, 800, 1000. So there is enhancement of the electric potential at every electrode, at every dynode. And the photoelectrons are pulled to these dynode 1, while a number of electrons are what they do is they generate secondary electrons. They are emitted from the primary electrons that have fallen onto those plates. Now these in turn are pulled to the dynode 2, 3, and 6 in succession, emitted for each primary photoelectron. So what's going on here is that these in turn, what they do is they are pulled towards these diodes in successive sessions, where the electrons are getting multiplied at every step due to the secondary emissions that are causing. And finally, a highly amplified electrical pulse is delivered at this anode, and wherefrom this electrical pulse is amplified, and after discrimination from the noise level pulses that may be present in the signal, it is given to the recording scalars and counters that exist inside this electronic arrangement. Now the point is that the transit time of electrons in this case, and the built-up period of photons in this scintillation counter is the time that it takes to fuel this signal is of the order of 10 to the power of minus 8 seconds. And the resolving time of the instrument depends on the RMS deviation in this time. It depends on the root mean square deviation of the time of 10 to the power of minus 8. This is of the order of 10 to the power of minus 6 in typical scintillation counters, which is preferably 10 to the power of 5 times better than that of GM counter. And the resolving time for GM counter is only 10 to the power of minus 4 seconds. And here we have, for the best scintillation, it is 10 to the power of minus 9 seconds. So we can see here that scintillation counter is proven to be better than that of GM counter, which has a resolving power of only 10 to the power of minus 4 seconds. Now the high efficiency of the detection that here we have short resolving time, we have linearity in response in the wide range of incident radiations. And these things are considered as the advantages of the scintillation counters, and this is what makes scintillation counter superior to the conventional GM counters. Now these are generally used for study of intensity and energy spectra of X-rays and gamma rays. And what we can calculate the percentage energy resolution. We can calculate the percentage energy resolution. Percentage energy resolution. And this percentage energy resolution is defined as the ratio of. It's defined as a ratio of full wave half maxima. Full width half maxima of the peak to the corresponding pulse height. The pulse height, say, that is Vp times 100%. So what this gives us is, it gives us the measure of energy resolution. And these scintillation counters, these detectors, have an energy resolution of the order of 8%. And these are extensively used in nuclear physics, spectroscopic studies, optoelectronics, material research, nuclear chemistry, and apart from the studies of cosmic radiations and elementary particles. So with this, I would like to end this video where we have tried to understand the mechanism of working of a scintillation counter, and what we found is that it has a better resolving time in comparison to GM counter, and it certainly does have higher efficiency of detection, and it is linear with respect to the incident radiations. This is what this scintillation counter, which is an electronic detector, it's counted to be the better counter in comparison to the GM counter in certain cases.